Hello, hello. We survived the summer. Hello,
Hey,
Thomas.
Luca, and hey, everyone.
Nice. Great. We're back. We're back. We thought we would just take a little break while we were in different parts of the world. We took a nice break and we thought about Thunder a lot. Well, not too much, but enough. And then we're back and we would like to uh, up until now, we introduced the concepts behind Thunder, behind deep learning compilers. We explored what JAX does, what Torch compile does, what Thunder does, and what a program transform is. But we did it Tapa style, right? So we got a taste for each of one of these things. And since we like doing things from first principle a lot, we thought that it would be good this time to take a simple model and go and create a kernel for it, and then replace the kernel, sorry, replace a part of the model with this custom kernel in such a way that it's as simple as possible. Let's say it's the hello world of Thunder. So people who wants to get into kernel development and so on, they can start following our stuff, and then we'll build up from here. Right, Thomas?
Yeah, and we will use an MLP, and then, yeah, we will see how to get the kernel, right?
Perfect. Yes, yes. All right. So just a quick intro, 5 minutes, and then we get into the code because we have a lot of stuff, and so we can follow step by step. But just the basic ingredients here. We'll do an MLP. What is an MLP? It just do we have bias, by the way, this time? Do you think we can use bias or
No, we
not?
don't
Not at
have
all. No
bias.
bias.
Being
Awesome.
unbiased
Even
is all
simpler.
the rage these days.
That's very true. So what this is that we have a linear layer, and so will you enter with a tensor x, and then you have weights, and then you multiply your inputs by the weights, you get some output, and then this output you go through a nonlinearity here, and then you get the output. So this is the simplest possible uh, multi-layer perceptron. Actually, this is a single layer
No,
perceptron.
you want a second layer, right? You
Exactly. To
want a
make it
second layer.
multi-layer, yeah, you want another thing, which is a second linear layer here, because otherwise it wouldn't be multi anything. Um, and then, of course, you can stack many of them, but we'll stop as soon as possible so that we have like, let's wait one and wait two. But the kind of unit is what I was showing at the beginning, which is what you can repeat over and over, and then you get the output of it.
Yeah,
And of course, if you do this
so
in
the thing is
PyTorch,
that you
yep,
need two,
go
right?
ahead.
You need two layers to make it useful.
Yep, okay. Let's do it two layers then. Okay, you have the output here.
We
So,
have two layers, so two mud modes.
and then, yeah, exactly. So, well, here, and then we have another nonlinearity in your example.
No, no, that's cool. Let's just go
Okay,
linear, non-linearity, linear.
exactly. Okay, that's cool. And then um, we will, so you can express all this in PyTorch using the PyTorch kernels, and PyTorch kernels usually are very fast, right? But then what we will do is we'll get our NN module, which describes this model, into Thunder, and Thunder will, by calling ThunderJIT, will generate our representation for this program, and then we'll define a Triton kernel for the linear part. So a matrix multiplication, like uh, and then the Triton kernel will replace or will execute some of the operations here. So this is high level what will happen right now. And if you know about that, Triton is a way to write custom kernels in a Python domain specific language. So it's very easy for people to get started with Triton, or not very easy. It's easier than using CUDA apparently, and then it's easy to integrate. So let's get directly into the code and follow through, and then we can stop along the way for explanations.
Yeah, so you could have made my life easier by saying we'll create a kernel for the nonlinearity, but yeah, apparently not.
We
So
like matrix multiplications.
yeah, so I started up the Thunder Live demo studio, and I upgraded to an L40 because we have shiny new GPUs, and this one is not too expensive, but quite neat. In particular, it has like a lot of RAM, not that we need it for the two-layer model, but
Yeah, yeah,
well,
48
cool.
gigabytes. Like for
So,
comparison, like A100s have 40 or 80 gigabytes, and L40 have 48. So it's quite sizable. You can do quite a lot of things with it. So that's great.
right. So let's import Torch and let's have our model that Luca just showed. So this would be Torch and then sequential, and that should contain a linear, oops, linear, say from, let's make a large one, right?
Yeah, we
From
have memory, so why not?
2048. This should be 96 probably, and we didn't want bias, right?
Right.
And then what's your favorite nonlinearity lookup? Relo,
Yeah,
Relo.
I'm old school, like ReLU, and then it's simple enough.
You're old school, but not 10H old school, right?
Yeah, yeah, no, that old school.
And here we have no bias either. So that's a co-model, but let's have it on the device. And just to make our lives easier, let's have this without the gradient part. And to make it maybe more interesting, let's have it in bfloat 16. And let's have a bit of input for it. Let's say, I don't know, batch size 64, 2048 inputs. And it needs to be of t-type torch bfloat 16 too, right?
Yep.
Okay, I can't spell. Uh, re no requires, not required.
Yeah,
Okay,
that's right.
so and we can thunderize it right now, right? Uh, Thunderize the model, send something through it, and then we had this thing that we could print the last program that it ran, and
Last
this was a
traces.
series of
Right.
last traces, right? Thanks. And we forgot to import Thunder. That is not
That's
good for
always a
this
mistake.
podcast.
Nice.
Right. And so here's our
Nice.
program.
Let's go
And we
slowly here.
see here,
Let's read line by line. So I'm interested in understanding
yeah.
every single one.
Okay, so apparently something didn't quite work out, and the requires grad should be false. Let's make
Oh
that
yeah.
because it looks a bit easy. Okay, so we have input weight, the first weight and the second weight. And then we have a functional linear call that was called from the module linear. And this can be decomposed into the call to the torch function and then to the thunder torch function and then to the primitive, but that's of not that much importance. Then the relo
Right.
got
Just
decomposed into,
yeah,
yeah,
sorry. Just to reiterate there, when we see decomposed, maybe it's good to mention that this is what semantically happens, but it's not that Thunder actually always decomposes these operations. All that Thunder is telling you at that point is, oh, look, this high-level torch operation actually means these other operations in terms of primitives. So whether those primitives will execute or torch will execute, it's actually up to the executor at the end to pick out whatever level they want.
yeah. So this has been like transformed by PyTorch. This is why here we're down to the decomposed version because NVFuser said, well, I can handle it, but give me the decomposed version. And then here's the second linear, and the result of the second linear T10 will be returned. And so that's our little Thunder program.
Yeah, and can
Okay, but
we look at the ReLU there? Because we saw a ReLU and now we see a GT and where. So let's spell it out explicitly. The ReLU
yeah,
is
we
that
can.
function that, right?
Okay, yeah. So relo is the function that checks is it like greater than 0, and if it is, it returns the value. So this is
Right.
the comparison result. And if it is, it returns the value, and if it isn't, it returns 0. So it's capped at 0. And if you want to see the relo, you can go back in the list of transformations. So this is this has also been transformed for execution, but if we take the one before that, you see that here we still have the relo.
Oh, there it is. Yes, yes.
And
And we
so
see
this
some
is,
conversion of type because, um, we expressed a number. Um, so what is the type conversion on the
this
zero
one.
element type zero? Yep.
Yeah, the type of the 0 seems to be implicitly float. And so this is converted to float. But yeah, it
Yeah, it's
will
probably
be
in
all
the
of,
in the primitive definition, right? That is
yeah,
float, statically float. Yeah, it's interesting. Okay,
yeah.
great.
Okay, so this is it, but let's look at how to get the kernel, right? You promised the
Yeah,
kernel,
yep.
and do you promise the one for the activation? No, you promised the one for the matmul. Okay, so
Exactly.
uh, let uh, let's do a Triton matmul. So import Triton, and you mentioned that it is a domain-specific language. And what does this mean in Python? So this means that there's like a language in which you formulate the expressions. And so this is called triton.language, and we import it as TL because it will appear quite often. Okay, and so with this, we can start writing our kernel. And similar to what Thunder does and other compilers, we can decorate things here with triton.zip. And then we need to define a kernel. So this would be like a matmul kernel.
Which is
And so
equivalent
we
to our
have in our,
linear. Yeah, just an explanation, which is equivalent to our linear, right, without the bias, essentially. And so we are
yeah,
writing this
there's
this
a,
operation there, just to be explicit.
yeah, so we could make this also a linear kernel, but let's use the matmul
Hmm.
kernel. And
Yep.
in all fairness, I have adapted this from the Triton tutorial on matrix multiplication. So all the good stuff is from them, and we're going over it here. But do check out the original too. Uh, so in Triton lang, there's this matrix multiplication tutorial that we base this on, a simplified version. So we have two operands, let's say A and B, and then there's the result. So these are I call them pointers, or the tutorial tools. So these are pointers to the tensors, or more specifically to the data space pointed to by the tensors. Then we need the dimensions. Typically, these are called M and K, right? So this is
Yep.
an M times K tensor, this is a K times N tensor, and this will be the result, an M times N tensor. So these are tensor sizes. And then we need all the strides. So stride AM, stride AK, stride BK. So all the tensors are two-dimensional, so they have two strides, and this gives you how many items you need to move in the memory to advance one row or column, right?
Exactly. So you have a 2D matrix. The stride will tell you that basically the stride for a simple 2D matrix when it's contiguous will be the number of columns and then one, because you will, to advance of one row, you will have to skip in memory, thinking about one contiguous, one-dimensional storage. You need to jump every row to get to the next row. And this is what the first stride is. And for the columns, if you move in a matrix column by column, you just need to advance by one. And so the stride there will be one. But then there can be variations on the theme, so you will be provided with the strides here to do these operations without
Right.
bothering how it is. Yeah.
Yeah, and then there's a thing where we need to set how much work a given Triton execution block, and I'm calling this execution block in square quotes because I just made that up, how much work a given execution block does. And so this is given by block sizes. Yeah, we have three of them, unsurprisingly, and they are labeled as const expressions here in Triton, which means that when generating code, they will be like constant. So they will not, in contrast to these things, they will not depend on the input size or stuff like that. Well, at least not directly. There's some caching going on where you could have it depend, but as you can see, we're going to skip this part and we're going to set some like interesting values already, but I wrote m 3 times less bonus, of course.
Yeah,
So
the
total
TLDR here is
3.
that Triton takes a program and says, okay, I have a huge matrix to multiply things on. And so you can express your program as only operating on blocks of the inputs. And so
Right.
it's a vector program, but it's operating on a subset of your domain. And Triton will make it like will launch it in parallel for you across all the blocks that you can
Yeah,
map
you
over
want
your
to,
domain.
Luca, you want to show like how you do a 2D matrix multiplication?
But I think we're kind of like tight on time, so I would rather um,
Okay,
do it here, and maybe we can show it at the end as a recap
okay.
to not lose time
So
here. Yep.
the first thing we have to like check is where we are. Um, Triton has the concept of a program ID, and this is like the ID of the execution block, as I called it. So it's called program here. Um, and so this needs to be held up for, we want each of these programs, each of these execution blocks, uh, uh, we want each of these to handle a certain square submatrix of the output matrix. And so we write here what we want to do here. And so obviously, if we have block sizes and we have the dimensions, then we need to get the number of blocks. We have the division of these, and we need to round up if we want to. If we have something that's not commensurate, so this will be ceiling division. And so we have like block size m blocks in the m direction, and this will be the fastest moving thing of the program ID, and then we have this in n direction too. And so the next thing we need is we need to know where to look in the input matrices. And so here Luca mentioned that Triton always like handles a block. And so what we do is we first calculate the offsets, and this will be like an entire vector. And so we have we need to have the right block. And this is the top left the top left row of the top row of what we need to access, and then this block will have a block size set of indices. So we built a vector here, at least conceptually, and then we like wrap it at n. And so the next thing we do is the same with bn, and of course here we just replace everything m with everything n, right? So we have the output column, if you want, and then the index, the top output column, and then all the columns that we need. And so this is this. And then we will proceed in terms of blocks in a for loop, but within each iteration of the for loop, we will handle block size k things. So the offset here is just block size k, and we're still in the 0th block for k, if you want. So these are the offsets, and then we can already move like the pointers to the matrix from a PTR to the offsets. And so we have the offsets in AM, and these need to be multiplied by the stride AM. And then we have the offsets in K direction. And you see that I'm inserting dimensions. So this is 2-dimensional and has a broadcasting thing going on. And we multiply this with the strides by AK. And so similarly, we have for B the same thing. And we have the B pointers, the B pointer, the offsets in K direction is here the slower moving one, and then this is times stride BK, right? And the offsets in N direction, and here we have this is the slower moving dimension 2, and so this needs to be multiplied by stride BN.
So what happened basically, right, is that we took our matrices, we divided the domains in blocks that our little program will run over. So it won't run over the full matrix, it will run over a block of each of the matrices. And then what we're doing here is basically, since our data is coming in a one-dimensional thing, we need to compute the offsets at which we get the data corresponding to those blocks so that we can do operations around them. So up until now, we haven't done anything. We're basically just got the address of where to get the numbers in the storage that we're getting for the things we need to compute. And it's a once you learn it, it's actually a simple mental model that you need to have. So I'm encouraging whoever is like uncertain about this stuff to read the Triton documentation and the tutorials there, because once you understand the flow of what we're writing, then everything will kind of flow. And then there are many other details there, but it's actually I'm encouraging people to dive in because it's once you have the right mental model, then it's quite approachable. So right now we have the pointers, which are where are the numbers of A and the numbers of B that fall into the blocks that we're interested in, so that now we can write vector operations for those.
Yeah, and so one maybe a bit of advertisement tomorrow at a bit of a later time of the day. Our friends from LinkedIn, they will give a talk on the Lego kernels, which is a set of very new kernels for LLMs in Triton. You can check it out here. Uh, uh, and so Byron will give a yeah, now I have messed this up, right? The URL that I get here. Uh,
And needless to say, we're in touch with the LinkedIn people to see how we can run their kernel with Thunder, and so
right.
it's very exciting.
Oh, I'm bad at
Yeah,
finding
you're
link.
sharing the notebook though, so it's no harm done. That's fine.
Oh, okay. I'm just sharing the thing. Okay, then I don't need to
You
open
don't
it
need to
in another tab.
apologize.
Yeah. Okay. So Luca mentioned that we want to compute something. So
Yeah, that would be nice.
let's get some space with the result. And before we have started computation, it's all going to be zero. And how many zeros will we need here? So I mentioned that each program will compute the block size m times block size n bit of the result matrix. So we allocate this here. And so for numerical accuracy reasons, remember we had bfloat 62, but so it's common to use higher
60.
precision data type, so float 62 for the operations here. And so this will be the result, and we reserve some memory for this. Conceptually 2D, but of course it's up to Triton how to compile it. And now I mentioned the loop over the K blocks, so let's do this too. And so we need like K divided by block size, K blocks of K in the K dimension to compute one result. Okay, and now we prepared all the pointers, and of course pointers are only good if you read from the memory space, so this happens with tl.load, and we read from the A pointers, and we can mask this in order to not read beyond the matrix, and so we only do this if we're still in the matrix, and if not, we just set the thing to zero. And unsurprisingly, we do the same for B. So we have the B pointers. The mask is slightly different because now it's the other dimension that is masked here, the first one in B. And so this is the same, though we don't want to read over our limit. Strictly speaking, probably we should also mask it for the for the for the other dimension, but let's not be too strict here. And now we can actually compute something, and so this will be tl.dot, which computes the like the current tile reduction. So this dot product here is over the k within a block, and so this is how you write this. And note that this is the only place where we actually compute something. And you will notice that this will remain the only place where we compute something. Okay, so the next thing is, in the next k iteration, we will want to look at different memory positions. So we need to move the a pointers by k. So this will be by block size k times, and now we need to multiply with the correct strides again. So nothing very spectacular, but it's a lot of pointer moving here. And it's a bit faster to do this with this pointer arithmetic thing, updating the pointers, rather than doing indexing every time. This is just how it is. So we computed the result in float 32. So we should cast it back to our target data type, which will be bfloat 16 here.
So
And
a single program right now will iterate over the whole k, and the k is the dimension. When you do row by column, is the length of the row of the first matrix and the length of the column of the second. So in this, we still do things in blocks, but we do it in the context of the same program, which is not interesting to see, because the kernel iterates sequentially, right, over the full row. And
yeah,
I
so
find
this is
this when you,
sequentially.
yep,
This is sequentially, but of course Triton has magic to do this here in parallel, right?
exactly, exactly. But the outer loop is sequential, which is interesting to me, right?
Right.
It's an interesting thing. But given that we are doing everything else in parallel, that doesn't hurt us. But there are optimizations that you can do to this, where you minimize the amount of loads you need to do, or you still do the same loads, but you do them more intelligently. And so you can even go faster with this. And load, just to
Yeah.
remember, load is where I have my data somewhere, not on the CPU, still on the GPU, but in slower memory, potentially, or in the cache. And I kind of grab all the values from the offset and I stick them into what represents A and what represents B, so that I can fast compute whatever operation, in this case, dot I make. And that has a lot
Yep.
of impact on the performance on the kernel, that operation alone.
Yeah, so this will be loading from global memory into shared memory if you want.
Yep.
It's a bit up to Triton how to do it exactly, but this is
Mm-hmm.
what happens. And so
Awesome.
by obviously here you have like this interleave between k, and so you try to not have like dimension to the third number of loads here. Um,
Mm-hmm.
okay, but so we have
Let's
our
go.
result. Now we need to know where to put it. And so
Yep.
we do the same thing with the offsets again. So this will be pit m times block size m plus tl.arange 0 block size m. This will be the offset in the m direction. And so the n direction is much of the same nature. So we have block size n plus tl.arange 0 block size n. And you didn't like save me here. This should be b. Um, okay, so then we have the pointers, and this is like the same as before. So we have the base pointer, and then we have the stride times the offsets, and this will be in the slower dimension, and then we have the stride times the offsets in the cn dimension, and this is the other dimension for the broadcasting. And now we have a mask too, and so this is if these offsets in n direction oh offsets in M
Yeah,
direction
the
are
mask will
these.
tell Triton where not to write or not to read. So it's kind of a guard
Right,
against
not to
memory
write.
access. Yeah, in this case, not to write. In the previous case, not to read. Yeah.
Right. And so all we need to do is TL store
Yay.
C pointers C and have the mask here. And so this should give us a kernel. It doesn't have any syntax errors, which is amazing. But now we have to call this program, right? And
Yeah,
so
exactly.
let's write a matmul function, and I could like check a lot of shapes, but M and K is one shape, and the other shape is K2 and N, and this is B shape, and we want that K2 is equal to K. And then we allocate some output. So all these PyTorch functions, when you don't like give them the memory place where it should go, they need to allocate an output, and this is no different. And empty here doesn't mean empty in the sense of no memory, but no values are defined, because otherwise we would have to fill the memory before going further, and it will be overwritten anyways. And so, strictly speaking, I should be checking the a.device is equal to b.device, right? If I could spell device, I would do that. And then we need to tell it a bit about the grid, and this is kind of the magic thing. It is like similar to this now tells us which program IDs we lambda with some metadata, and the metadata will be a magic dictionary that Triton passes to this function. And so this gives us how many programs we need. And we know this is like for the columns we needed, and this was given by the size in M direction divided by the block size. And then we need to multiply this by the same expression in the N direction.
Yeah, we often talked about blocks here where a program only executed on a certain block and so on. This is what it means. Like we initialize as many programs as needed to launch them all in parallel. And then each program operates into a block, and the operations they does, like dot, will also be in parallel. So there's a lot of parallelism here, which is what GPUs really like.
Right, and now we need to pass basically the same things as before. So these will be the tensors, and this will be translated to the tensor pointers. This is the sizes. They will be given to the kernel, and we wanted the strides, right? And so this is a bit tedious, but we will manage.
Yeah, so here, remember we had to have the strides to compute the positions inside the linear storage where our values is. And we're getting those strides from PyTorch essentially, because PyTorch has the same kind of memory model underneath. It has storage and it has strides, and then we can just access the value of those strides and pass them to Triton.
Oh, I'm spelling things again. Okay, so let's try it out. Torch the random 2048, 4096, and we want the device as CODA, and D type is torch bfloat 16, and for B we have much of the same, except the dimension will be well, we had 64 and 2048, right, as the input. But this will not work. Let's swap this. Um, and now we can multiply those, or try to. Matmul AB, and oh no, offsets n is not defined. So where did I use offsets n? Offsets n, and I called it bn. Okay, so it gives some
Nice.
result,
Amazing.
but the question
Yeah,
is,
so what
will
happened
it
right
be?
now is that the Triton compiler, so the Triton passed that representation of the program that we had, the source code, to something called LLVM, which is a compiler or a tool to build compilers. And that thing compile, and it's very common. So a lot of C++ compilers. It's a very popular project where a lot of compilers are based on it, and Triton is no exception. And then it produces PTX directly, so it doesn't go through CUDA. Just for whoever is curious, it doesn't translate whatever Thomas has written into a CUDA kernel. It generates the what CUDA generates as well, which is a lower level representation of the program that gets translated again into lower level before it gets executed by the GPU. It's called PTX. It's not something you want to write by hand.
Yeah, it's like higher intermediate level assembly for CUDA. But so right now we're like 10 times as slow, but it's on a very slow basis. So there's an auto tuning function for Triton, which usually is used, and then it will like tune things like magic parameters. And so if we supplement those manually, then we run out of memory.
Yeah, it's Num
No,
Warp,
it's
I think, not Wrap.
non-warps.
Yeah, Warps.
Yeah, never do this live. Okay, so we can time these, and it's running a bit. Yeah, that got 3 times as fast, right? It's still 3 times slower, um, but depending on the input size, if I enlarge this here, let's say I'm doing 4069 here, then we find that it's getting pretty close. And this is not like it's within 10%. And
Yeah,
that's
it's
not
crazy,
like the
right?
best optimization that Triton can do,
Yeah,
right? So there's still
yeah,
a
exactly.
bit of trick to get it faster.
I mean, this is kind of the
Okay,
hello world of matrix multiplication, so it's kind of crazy we get so close. But yeah, that's great.
yeah. Uh, And you could have just said we're doing a kernel for the for the activation function, right?
Haha,
And this
that was
is
a great
mapped to
journey.
our model.
Yep.
Yeah, remember that we wanted to do a thing to replace the standard linear layer with our own. So we will define an executor, the matmul executor, and this will be Thunder executor. We saw this, I think, in one of the earlier sessions already, but so Thunder is very extensible. This is one of the 3 things I'm particularly proud of, and probably most people involved in Thunder as well. Um, and so we define a meta function, which basically says if you give me this kind of a tensor with this kind of metadata, I'm going to produce one of that. So it's like A, but the shape is different. So it's A shape 0 times B shape 1, right? That's
Yeah. So
the
we're
thing.
promising that the shape of the output will be that, which is what the matrix multiplication produces, right? We said n by k times m. So it's going to be n by m, which is what this meta function is saying, is telling Thunder.
Right, and the implementation will just call our matmul function. I could have probably called it directly. And now we register the operator here with our executor, and so register operator, and we call it my matmul. It's not very creative, but yeah. Meta will be our meta function, and the actual function will be the my matmul implementation. Okay, so we can do this, and now my matmul is what we call a symbol, which is kind of a fancy talk for a function that you can call in Thunder. But now we wanted to replace the linear layers, and it's not quite a matmul layer. So we have to tell Thunder like how to translate this. So a linear layer, if we scroll up a bit, we saw that the linear layers had 3 arguments, right? So here we had the input, the weight, and the bias, which was none. So we need to define a function that takes these 3 and changes them. Why can I not click here? Sorry. Okay, let me just use. There we are. Okay. So I need to have my linear, and I want to transform it into the matmul, right? And so I have the weight, I have the bias. I want to have bias is none, and then I can just return my matmul input, and then the weight doesn't quite fit, but we need to transpose it, right? And we can say which linear layers we want to, and I misspelled transform. We can say which linear layers we actually want to take, and so this is a function that takes the arguments and now says whether we want to have it. So if len input shape is equals 2, so we don't do any batch dimensions, and len weight.shape is equals to, I think this is always the case in PyTorch, but whatever, and bias must be none, and then we return true, and otherwise we return false. Of course, I could have just returned this expression as a Boolean too. And then with these 2 functions, we can register our thing as an implementation, and this will implement torch and then functional linear. I took this from the trace, and the
so this needs to be, this doesn't need to be necessarily a torch operation or anything. It needs to be a symbol that appears in the trace. So you can say, okay, when I see the symbol in the trace, then I'm gonna execute this other thing, right? Or this other thing, this thing, because there could not be something that executes a certain symbol. And so we're just saying, okay, whenever you see the symbol in the trace, use this implementation. So it's very straightforward.
Yeah,
but
and this could
only
be either
if
reference to the. Sorry?
Yeah, go ahead. No, I mean, I was saying only if the checker returns true. If the checker, if it's the same symbol, but the checker returns false, then leave it there, because we don't have an implementation for something that has a dimension greater than 2. So we have a lot of flexibility to choose whether to pick up that symbol from the trace for execution or not. And so this way we can dispatch a trace to multiple different executors, and that's what makes Thunder an interesting story if you want to have leverage to optimize your models.
Right, and now we can check if it still works. And it does still work.
It's amazing.
And now we can admire the last traces. And I will not forget the S here of JM. And we look at the last one that has been transformed for execution. And here we see that it's like calling my matmul. And so if we want to, and it calls my matmul here too. And actually the permutations have been moved up, but that's not of importance to us. So it has automatically replaced the linear layers with whatever we told it here. And what we told it was to replace it with my matmul with input and the transposed weight. What we can also do to demonstrate the checker, we could like only have one bias. And
Yep.
now, of course, if we compile our model again, and sorry about the scrolling here, Luca always tells me not to scroll, and I'll do it nonetheless.
Well,
And
how can
now
you
we
not do
see
it
that,
right now? It's impossible.
yeah, automatically we found that here where we have an actual bias, we said, nah, thanks, via the checker function. And here where we don't have a bias, we actually said, yeah, this is ours. And so this is how registering the operators and the checker functions work. Once you have those optimized kernels, and of course that is art and science, and thanks Luca for bearing with me walking through this very slowly.
No, it's great. I think it was a great end-to-end journey, right? Because now I have the bug of, let me see if I can actually beat standard PyTorch on these particular sizes. And, keep in mind that certain optimizations will work on a certain range of sizes. So writing one single kernel that can be faster across all things is not very simple, but actually that's not the point. Like PyTorch itself has a lot of kernels for the same operation in different ranges of sizes. And so what you can do here though is, since you know your workload, you know your inputs, and you know what you need to optimize for, you have a lot of leverage to actually go in and make things super fast. And so in the spirit of keeping the framework thin, we will explore all the different extension points during the next few episodes where, for example, we could manually fuse two operations. Now we could do the matrix multiplication and then fuse it with a nonlinearity directly, so we don't have to communicate with memory, and we can just do things in one shot. And so I think this is a great way to start after the summer. So thanks so much, Thomas, for the ton of code that you wrote with just like one
Yeah,
or two, typos. It was crazy. So thanks a lot, and yeah, have fun, and see you next Friday, Tom.
yeah, and you have a good weekend, both you, Luca, and everyone who has been watching. Thanks. And if you want
Thank
more
you. Bye bye.
Triton, check out CUDA mode tomorrow.
Yeah,
And
could have tomorrow.
next
Maybe
week,
next week, or maybe the other week or next week we can do some Liger kernels to demonstrate the whole thing. It's the same principle, just that the LinkedIn people writing Liger spend a ton of time, writing them just right so you can save memory and go faster with LLMs. Okay, great. Thank you so
yes,
much.
let's do that next week, same time.
Bye bye.